Hello. So today I'd like to discuss a reaction from chemistry, particularly organic chemistry. It will be from the lesson of carboxylic acids and amines. It's actually a method of preparation of amines. It is called the Hoffmann bromamide degradation reaction. It has a very characteristic mechanism of its own. It's a very interesting mechanism where intermediate of isocyanate is formed, but the formation of isocyanate is a very interesting part in the mechanism, and there is a bit of history about it which we will discuss when we start writing the mechanism of the reaction. So this is going to be a different video, like it is not something like problem solving. Instead I will be explaining the concept and how a small discussion regarding the mechanism or a small debate regarding the mechanism was clarified through history. Okay, so let us start. First I'll write the reaction itself here. So I'll write the reaction. Okay, this is a method of preparing amines from amide. Okay, so what is the difference between amine and amide? That is the first thing we need to discuss. So let me take my pen. See, C double bond O NH2. This is an amide. Okay, so carbonyl group is present, and an NH2 group, amine group, is attached to a carbonyl. So this is what is known as amide. Now, what is an amine? See, this is an amine. This is a primary amine. Let us not go into detail. Primary means CH2 NH2. Only one carbon is attached to the nitrogen. Secondary means two carbon will be attached to nitrogen. Tertiary, three carbon to nitrogen. Okay, let us not go into detail, but this is what is called an amine. Okay, carbonyl is not present, it is substituted by hydrogen. Okay, so this is the basics. So the reaction is preparation of an amine from an amide. So this is what happens during Hoffmann bromamide degradation. Okay, I write as HBD. This is just to give you an idea what an amide and an amine is. Okay, now let us move on to the reaction. Let me clear this here. Okay, so we'll write the reaction here. RCO NH2. It's a double bond, by the way. RCO NH2 plus Br2 plus KOH. So we are reacting an amide in the presence of a halogen. Here I have taken bromine and a base KOH, which will give us RNH2. It's a degradation reaction, aptly termed, because one carbon is reduced. See, C double bond O is removed. It just becomes RNH2. So the chain length is reduced by one carbon. So RNH2 plus, naturally, C double bond O, you can think of it as escaping in the form of carbon dioxide, which reacts with the base present in KOH and gives CO3 minus, carbonate ion, sorry, CO3 2 minus, plus KBr plus H2. Okay, CO3 2 minus, I can write actually K2CO3. Okay, anyway. So this is the reaction, basic reaction of the Hoffmann bromide degradation. Now, the mechanism is where things get interesting. The mechanism is a multi-step mechanism, and the confusion arises where which step can be determined to be the rate determining step, RDS. Okay, anyway, we will come to that. First, let me start writing the mechanism here. So this is the reaction. We'll keep it here, and I'll move a bit down, and we'll discuss the mechanism. Right. This is what I like about organic chemistry, by the way. Writing mechanisms, it's like understanding the psychology of molecules, how they react under different conditions, how one molecule sees another molecule, how it attacks the system. It's very interesting. So let us go to the mechanism of the reaction. It is a multi-step reaction, by the way. So it takes place in many steps. Here I will be writing it in the form of 4 steps. Okay. So the first step involves the attack of bromine on RCONH2. Okay. RC double bond O 2 attacks bromine. Okay. There is an internal mechanism in for this step itself. So I'll show that too. But first, let me write the first step. Yeah, to give R C double bond O NH Br plus HBr, as you can predict. But again, note the HBr so formed here reacts with KOH to form KBr plus H2. Okay, this is how the product KBr is formed. The single step actually has a deeper mechanism inside, like I'll just show you. It's a simple mechanism here. I'll write it in brackets. Okay, see, R C double bond O NH2 is first attacked by a base. I'm writing it as OH minus supplied by KOH. So OH minus abstracts the acidic proton here, which is attached to nitrogen to give R C double bond O NH negative charge. So this is a nucleophile now. The nitrogen here is highly electron rich and it is ready to attack a species which can accept the electron. Okay. So which species do we have? See, organic chemistry always you should remember. You should not consider just that single step or just that single reactant or product. Always keep in mind the entire contents of the reaction or contents of the vessel. Entire thing comes into picture. Okay. So here we know bromine is already there in the vessel. We are supplying bromine. So bromine being an element of the third period, that is not the first two halogens, uh, that is fluorine and chlorine. Bromine has a d orbital, has an empty d orbital which is ready to accept electrons. Okay. So yeah, that is how it comes. It is the third period, right? No, fourth period. Okay. So fourth period element, it has the d orbital. So this can be ready to accept the electron supplied by nitrogen. So nitrogen attacks bromine. So what I'll do is I'll write it here plus Br single bond Br. This is how bromine is. And there is a vacant d orbital. Both bromine have it, but I am just marking it for one bromine, which is being attacked by nitrogen. Okay. So the lone pair of nitrogen or the negative charge in nitrogen attacks the bromine, donates the electron to the d orbital of the bromine, and this forms R C double bond O NH Br. Okay, so again this bromine is a good leaving group Br minus. So 1 minute we will have, and we get R C double bond O NH single bond Br. So this is the product we got here. So there is an internal mechanism here. It's not just a single step, but I can write it this way. It's actually a very easy step. Okay, no need to go elaborate here, but the real part of the mechanism comes in the third and fourth steps. We will come there. Okay, now we will move on to the next part of the mechanism. Right. Now step 2 of the mechanism is the formed product, which is RCO NH Br is attacked by OH minus again, once again. So 1 minute. I'll just erase this. That's right, OH minus here plus OH minus, giving again the proton here of NHBr is highly acidic and shall be abstracted by the base, which is OH minus. Okay, so we get R C double bond O N minus Br plus H2O. Right, this is the second step. Now we'll move on to the third step. And as all of you might have predicted, seeing the product here, it is easy to identify the third step, as there is a Br here, bromine here, and nitrogen has a negative charge. Br minus, being an extremely good leaving group, will definitely go from here and will form Br minus, and you will get a nitrene. Okay, not a carbene, a nitrene. Okay, so I'll write it here. So step 3 of the mechanism is R C double bond O N minus Br, giving Br minus goes away, giving R C double bond O N lone pair. Okay, so we get a nitrene here, and definitely Br minus goes off, and again this Br minus can react with the counter cation K plus to give Kbr next mole. Okay, that is a byproduct. No need to worry about that now. Now, kindly remember this step, the third step, as it is very important in our discussion, and we'll go on to the fourth step. Okay, this is the last step of the mechanism. I know till now it seems very easy, but a lot of confusion is there ahead. Okay, so RCON, the nitrene so formed, undergoes rearrangement. Okay, so what happens here? The R part comes and attaches to nitrogen, while this lone pair gets transferred here. Right. So this forms C double bond O, double bond N, single bond R. Okay. This product so formed is called an isocyanate. Okay. I'll write it here. This is isocyanate. Okay. Now comes the major problem. Like, every mechanism must have a rate determining step. Every reaction must have a rate determining step. In a single step reaction, the same step is the rate determining step. The rate of the reaction, we come to kinetics here, the rate of the reaction is determined by the rate of the rate determining step, and the RDS will be the slowest step in any reaction. Now, in case of a multi-step reaction, only one rate determining step is possible, and all the steps before the rate determining step are equilibrium steps, that is reversible. Forward and backward reactions are possible. The steps after the rate determining step is an extremely fast step. Okay, it happens very quick that it is not considered in kinetics. Okay, in this reaction, we need to determine which the rate determining step is. Which step the rate determining step is. We know that the rate determining step is where usually the most difficult species is formed. The most unstable species, the most difficult species, which is extremely difficult to form from an energy point of view, that will be the rate determining step. The problem is here two such species are formed in two different steps. Nitrene formed here is an extremely unstable species because nitrogen is electron deficient, only 1, 2, 3, 4, 5 electrons, octet is not complete. So third step where rearrangement is happening, Br minus is leaving, RCON, not rearrangement in that sense. RCON is formed, a nitrene is formed. That is a possible contender to become the rate determining step. Whereas in the fourth step, where such a huge rearrangement is forming to form isocyanate, that is also possible that it is a rate determining step. So 3 and 4 both cannot simultaneously be the rate determining steps. Only one can be the rate determining step, and a lot of discussion has gone into this. Now anyway, I'll just complete the mechanism and we'll go into the evidence for the mechanism. Now the fourth step, we know isocyanate is formed, and upon further hydrolysis, H2O. Uh, 1 minute, let me change the color. Upon further hydrolysis of isocyanate, we get actually OH minus comes and attacks here, C double bond O, and another OH minus also attacks, giving us C double bond O, OH, OH, and again it is removing, it tautomerizes to form CO2. Okay, I am not writing the entire mechanism here because it will become very lengthy then. So it will form CO2 plus NH2R, that is RNH2, amine is formed, primary amine, and again CO2 formed in basic medium will give CO3 minus 2 minus plus H2. Okay, this is from where K2CO3 forms. Now we will come to the problem, like third step is the rate determining step or fourth step is the rate determining step. But before that, we will look at some evidence for the mechanism. Let us consider the fourth step to be the rate determining step. If fourth step is the rate determining step, then the stability of the carbanion R minus, which is shifting towards, or not carbanion, I should say, the electron density present in the alkyl group which is shifting towards nitrogen determines the rate of that step. Okay, the electron richness of the alkyl group which is shifting towards the nitrogen will determine how fast that step is. I'll give you the example. I'll give you the experimental evidence from which we can determine this. So what I'll do is I'll move this. We'll come back to the mechanism. So we'll go to experimental evidence for step 4. For being RDS. Right determining step, I am writing it as RDS. Okay. Consider the following. We'll take a few species here, like Latin group. Let us consider benzenamide undergoing the same reaction to give aniline. This is the first case, A. Second case, we'll consider a substituted ring, para substituted ring with an electron donating group, EDG. We'll consider an ether here and the same species, amide, to give a para substituted aniline. We'll consider another reaction again, but this time instead of an electron donating group, we'll consider an electron withdrawing group. Right. So we'll take, say, nitro group. Yeah, we'll take a nitro group here. Nitro group is an electron withdrawing group. So minus R group, that is the technical term. So this is a plus R group, this is a minus R group. Again we get a para substituted product. Now let us label each one of these as the rate constant to be K1, K2 and K3. The rate constants of the respective reactions are K1, K2 and K3. Through kinetic analysis, scientists were able to determine that the relative order of the rate constants to be K2 greater than K1 greater than K3. This was experimentally determined. Keeping this in mind, we are able to conclude that the electron richness of the alkyl group being transferred to the nitrogen in the fourth step is what determines the rate of the reaction, because as a decrease in rate was observed when the electron density in the alkyl group, here the aromatic ring was decreased, a decrease in rate was observed, and therefore it can be concluded that the fourth step should be the rate determining step. Clear? So researchers concluded that the fourth step should be the rate determining step, and the third step would then become an equilibrium step. So I'll write it here, implies as the electron density in the alkyl group, not in of the alkyl group increases, the rate increases. This implies, let me move. Yeah, so this implies step 4 is the rate determining step, right? So this was the experimental conclusion scientists came to after they studied the reaction or reactions of these three compounds, and they clearly understood the electron density in the alkyl chain influenced the rate of the reaction, and therefore step 4 was claimed to be the rate determining step. Now again a problem arose, because if step 3 is not the rate determining step, then a few products are possible. I'll show. See, let me move again. See, I'll move to step 3 once again. I'll show you here the nitrene formed. Okay, nitrene formed if step 3 is not the rate determining step, can be attacked by water present in the container. Okay, if it was an equilibrium step, if reversible reaction was possible, the water produced here can actually attack RCON, that is nitrene, and it can form an acyl hydroxylamine. Okay, I'll write this here. So this was a big problem in the mechanism proposed. I'll show it here. See, here we got the evidence that step 4 is the rate determining step, but I'll write it as problem. See, if step 4 was the rate determining step, then step 3 is a fast equilibrium step. I'm writing it as equum. So equilibrium step. This implies attack of H2O on nitrine is possible. Okay, I'll write it here again. See, if attack of H2O on nitrine is possible, another product will be formed, which is R C double bond O N, in the presence of water will give you R C double bond O N H O H. This is called an acyl hydroxyl amine. An acyl hydroxyl amine can be formed. Now, none of the experimental evidence shows that even 1% of such a product is formed in the entire course of the reaction. So this means step 4 cannot be the rate determining step. If step 3 was the rate determining step, this issue wouldn't be there. But again, the other problem would come into picture, like the electron density which influences the rate of the reaction, the electron density of the alkyl chain. Experimentally, it is proven that it influences the rate of the reaction. But if step 3 is proposed to be the rate determining step, step 4 cannot influence the rate, and this is a contradiction, huge contradiction. So this was the problem which scientists faced while trying to understand this reaction. So not even a trace of acyl hydroxylamine was formed, but at the same time, the electron density in the alkyl chain, which was being transferred to the nitrogen in step 4 of the mechanism, greatly influenced the rate of the reaction. So what is the conclusion? How do we understand this reaction? What is the actual mechanism? Later it was proposed that the solution came that step 3 and step 4 are not two different steps but are the same step. So entire problem is solved. If step 2, 3 and 4, that is the formation of nitrine and the rearrangement of the nitrine into an isocyanate, are taken to be the same step, entire problem is solved. So what happens is, actually, from later studies we were able to understand this. Let me move even further. I'll write it here. This is a very great discovery, that for understanding rather, that step 3 and step 4 are not two different steps but happen in one go. Okay, so this is where it gets interesting. If both are the same step, a transition state is formed, a cyclical transition state is formed. So what we'll do is, we'll write it as R C double bond O N negative charge Br. Entire thing happens as a single step. I'll show it here. Br minus leaves, nitrogen shifts its electron here, and at the same time the entire carbon chain, Entire carbon chain rearranges here, giving us R N double bond C double bond O plus Pr minus. This is the beauty of the reaction. This happens to a transition state. Now, which is the transition state? I will again draw the transition state here. See. By the way, this is the rate determining step of the reaction. R, B, S. Entire process happens in one single step. And this is possible only through discussion and debate of two contradicting experimental evidences. Okay, this is where it gets interesting. So what happens is a transition state is formed here, like I'll draw bonds being broken and bonds being formed in the form of dotted lines. N, dotted line, BR, dotted line, R, dotted line. N. So a cyclic transition state is being formed here with a negative charge dispersed throughout the ring, and this is where we get the isocyanate as the final product. So a cyclic transition state is formed in this reaction, and many other experimental evidences then later proved that in fact a cyclic transition state is formed. Now how can we prove a cyclic transition state is formed? The experimental evidence comes from two competing reactions. I will give you the entire reaction. When you take two different amides, one which is isotopically labeled nitrogen and which is one where nitrogen is the normal nitrogen N14, and we react both of them in the same container in the presence of KOH, the product formed confirms the presence of a cyclic transition state, and this proved the entire mechanism, that the fourth and third steps of the mechanism are one and the same. Okay, I'll give you that evidence too. See, the next experimental evidence for cyclic transition state. Okay, this is a very interesting evidence, and in fact it is a JE advanced question, previous year JE advanced question. So it goes really deep here. Like, you take two molecules, I write it in white. You take two molecules, one which is a normal benzamide and another which is an isotopically labeled benzamide. And also I'll probably put in a para substitute like CH3, methyl substituted benzamide, and we'll do the Hoffmann bromide degradation reaction. Question is, what is the product? Okay, so we have many options here, like option A, it can be normal aniline. Option B is it can be the isotopically labeled nitrogen and a para substituted aniline, and option C can be a crossover product, that is both can interchange with each other and forming NH2 here, that is the non-isotopically labeled nitrogen 14 along with the toluene alkyl chain or benzene ring. That is, in the fourth step we saw R group, that is alkyl group, is being transferred to the nitrogen. So here intermolecular transfer is being is happening. Okay, instead of intramolecular, intermolecular transfer is uh, being done here. So we are getting the non-isotopically labeled nitrogen here, that is not in 14. 1 minute, did I mark labeling here? No. See, this is the point. This is a labeled nitrogen atom. Okay, so crossover product is formed in option 3, and similarly option 4 is also a crossover product, like simple aniline but with nitrogen 14. Not nitrogen 14, isotopically labeled nitrogen. Now, this is where things get pretty clear, like why the cyclic transition state was taken as the actual mechanism. In case of the cyclic transition state formation, only intramolecular reaction is possible. It is an intramolecular rearrangement taking place. The alkyl group is being transferred in the same step as the bromine is leaving from the nitrogen. In the same step, N is rearranging its electrons. So if third and fourth steps are the same step, what happens is crossover products are not possible. Crossover products will be possible only if 3 and 4 were different steps and attack was possible in both steps. The product formed can attack the other reactant and so forming the crossover product C and D. But since intermolecular reaction is not occurring, since cyclic transition state is being formed, and since intramolecular reaction is more favorable, only products A and B were formed. C and D did not even come, like trace of C and D were also not formed. Therefore, it was a direct proof of, or it was a direct experimental evidence that the reaction happens in form of a cyclic transition state. Mechanism involves a cyclic transition state, and crossover products cannot be formed. So I'll write it here. Clearly I'll write it. See. The reason is C double bond O, dotted line R, dotted line N, dotted line bromine. This is the transition state formed. Intramolecular rearrangement. Not intermolecular. So if intramolecular rearrangement happens, A and B possible. Therefore, as intermolecular is not occurring, C and D not possible. This is a very deep mechanism, and there are many other reactions which follow somewhat similar mechanism, like Claisen rearrangement, Claisen-Schmidt condensation, etc. Let us not go into details, but wherever isocyanate is formed, wherever such mechanisms are followed, they are extremely interesting because of this small confusion. And finally, the confusion was resolved by combining both steps into a single step, which forms a cyclic transition state. So crossover products are not formed. This is a very important experimental evidence. Crossover products can't be formed. So this was the final step. This is how we determined that the cyclic transition state is formed, and third and fourth steps both are combined to form the rate determining step. So what I'll do is I'll go back to the mechanism and I will mark third and fourth steps to be the same. Proven to be same step. So it's a three-step mechanism, and it's an extremely interesting mechanism. I hope you got the point why it is such an interesting mechanism. Lot of experimental data has come into picture, lot of chemical reactions, lot of studies. Finally, we understand third and fourth step are the same step. I know this has been a long video, but I hope you enjoyed it. Keep wondering and keep learning. Thank you.